Okay, so this is a follow-up from the earlier video on confidence intervals, a particular example, an old exam question from Edexcel S3. It's a 99% confidence interval, and the idea is we've got a sample of 206. We've got a sample with mean 266 with standard with a sample size of 40, and basically what range do you think we can the mean can be? The key here is that the mean is unknown, so we have an unknown mean mu. We have a known standard deviation of 20 of the original distribution, but let's think about the sampling distribution. The sampling distribution will be normally distributed with, because it tells us it's normally distributed with mean unknown, but with standard deviation 20, so variance 20 squared divided by the 40. Okay, so that actually gives a standard deviation as the square root of 20 squared over 40, which is 20 over the square root of 40. It's the standard deviation, or the standard error, sometimes called the standard deviation x bar standard error. Okay, so when working out confidence interval, I personally, rather than just quote the formula, which many of you will remember the formula, but I personally tend to, because, you know, let's face it, we have a lot of things to hold in further maths. We might be thinking about all kinds of things that we have to do to get the full qualification. If you're doing mechanics, you have to start thinking about circular motion and lots of other things. So it may be that, you know, this is a relatively small part of what you know in further maths. So you need to perhaps cut down what you actually have to remember to a minimum. So what I always come back to is this: the transforming the sampling distribution to the Z distribution, where Z has mean 0 and standard deviation 1. Okay, and now we can get percentage values for the Z distribution either from the calculator or from the tables that are given in the formula book. I'll show you both. Anyway, we want a 99%. We want a 90% 9% confidence interval. So let's look at what values that gives us on our Z distribution. So we want it basically so that we've got 0.5% there and 0.5% there, so that we have in the middle here 99% in the middle. So we want to know what the Z value is here. Obviously that one will be the negative of the other. So we want to find out what that value is. And they say they're given in the formula book, or we can use a calculator. So let's use a calculator first. To get the Z value from there, we need to go to menu 7. And it's the inverse because we're working backwards. We've got a proportion, probability or percentage or whatever, and we want to find the actual value along of the actual Z value. So 3 here, I've got 0.99 here from a previous question we were doing. Obviously we need it to be 0.995 because we got 5% each, 0.5% each side. The standard deviation is 1 and the mean is 0. So that gives us the value 2.576. Okay, and then so therefore this is minus 2.576. Let's say if you prefer, you can use the tables. Here the 0.995 value there is written in the tables, but some people are so used to doing a calculator they might get there quicker than seeing the thing in the book of tables that you're given in the examination. Okay, so that's the Z value we're going to be working with. At that point, I like to just write out that as a probability statement. probability of Z lying between minus 2.576 and positive 2.576 equals to 0.99. Right, so we basically want to transform this to a confidence interval for mu, the unknown population mean. Right, so we're going to use this. Now, rearranging that, you might want to play around with that and rearrange it separately. It's best not to get too bogged down with inequalities, but if you rearrange that formula, you should, without too much bother, see that rearranging that to that formula should be mu equals to x bar minus the whatever the z value is times by that. But of course the value of z will be plus or minus, so we can just put a plus or minus there to get the formula for the confidence interval. So you're just rearranging that to get our formula for the confidence interval. So I'm just going to rewrite this thing here now. Let's just do it in 2 stages. But as I say, I'd urge you not to play around with the inequalities, because what's happening is the inequalities swap over and something strange, well not strange, something a little bit fiddly happens if you really want to be technical with it. So it's best to just write as little as possible, but not write anything wrong, because that's not good. So let's put x, so our sample mean is 266. Take away this unknown population mean, divided by the standard error, which is 20 over the square root of 40. 2.576 equals to 0.99. So rearranging that and say just put it into this format here, that gives us a probability that mu lies between 266 minus 2.576 times by 20 over the square root of 40, and mu lies between, and also the upper bound is 266 plus this z value times by 20 over the square root of 40. Okay, and if we work those out, the values we get are 257 or 258 to 3 significant figures. Let's be a bit more precise. 257.886, and the upper bound is 274.12. Equals to 0.99, and this by definition here is our confidence interval. So you can write in various ways, in words or whatever, or I'm going to write it confidence interval at 99% is that mu is a member of 257.86. Let's go for 257.9, and the upper bound is 274.1. Okay, so that's a confidence interval for mu at 99%. That means we don't know the mean. We can't be certain it lies within this range, but 99 times out of 100 samples of this kind, of 40, if we take the sample, then 99 of the, let's rephrase that, if we take samples of 40, 100 times, then on average we would expect one of those samples this interval here to not catch the mean. So there's a 1% chance it doesn't actually lie within that, but we can be 99% confident it does. Okay, that's it. Hope you find this helpful. Bye.